So we're going to go through the objective 3 out of the balancing ILM. This is the one where we're going to describe the single plane method of balancing using vectors. So the goal of balancing is to measure the amount of imbalance, determine the balancing weight to add or remove, and then find out where to add or remove the weight, and then to accomplish this in as few run-ups as possible. So this isn't always just kind of like a measure it and get it exactly perfect on the first time. Sometimes it takes a few adjustments to get it to within tolerances and specs. So with the balancing in the shop that we're going to do, I'm going to ask you to try and get it as close to perfect as possibly can. But sometimes it will take a few tries to get there, and that's common for even most experienced balancers. It takes them multiple tries to get it just perfect. So the vector diagrams used on the computer balancing programs are done on something called polar graph paper. So that's what we're looking at here in this slide. So at the top is your 0 or 360, and then there's these numbers that come all the way around back to 360. That is going to be a stationary measurement that you're going to see in the shop anyways. Then on the end of the shaft where you're going to be mounting the weights, there's a little bit of there's like a stationary angular measurement around, but the polar graph paper that you're going to use that I'll have printed off for you looks like this. And so this is the kind of the graph paper that we're going to use for calculating out and figuring out these vectors. Okay, so the vector is a line. What is a vector? A vector is a line whose length corresponds to the amount of, in this case, vibration, and whose direction corresponds to the phase angle. So just kind of to give you an idea of vectors, vectors are lines that are kind of proportionate in their drawing to something that's like actually like applicable. So let me I'm going to draw a little picture. Okay, so the picture is a river. Okay, so this is just kind of a rundown on what vectors are. Okay, so let's say that this is a river, and the river is flowing down in this case. And then let's say we have a mech tech student. Actually, I'll put mech tech student. We have a mech tech student up here that wants to get across the river. So we give this mech tech student a boat and the paddle, and we tell this mech tech student that he's got to go across this river. So the vector that he's going to be paddling at is actually directly across this river. But what we don't realize is that the river has a current itself. So the river is actually going to be pulling him down in a vector of this direction. So the actual vector of travel that this mech tech student is going to take is actually going to be somewhere down in this direction. Okay, so we have a vector of, this would be vector mech tech student. This would be the vector of the river, and then this one here would be the vector of travel. So by using this vector, and then looking at where you're going to end up, where the student ends up down here when he's finished crossing the river, you're calculating based on the kind of lengths of the lines and relative to each other, and these are vectors. Okay, so I just wanted to touch on that, just because if you haven't worked around physics or vectors or any of those things, that's what it is. That's what a vector is. So in this case of balancing, we're going to be looking at this vector. So this would be we're going to have balance where we're going to measure, and you're going to say, okay, here's a vector of the imbalance, and then we're going to add a trial weight, and then that trial weight is going to give us another vector. So let's say like over here somewhere. Okay, and then we're going to have to figure out, okay, well, this length of this line between here and here, what is the distance between there and there proportionate to these ones? And then we'll have to add that weight, relative to where we added our trial weight. And I'll get into all the steps that we're doing, but that's essentially what we're doing is we're saying, okay, if you have 5, 10, 15 mils of displacement at 50 degrees, and then we add our trial weight, and now the new imbalance is measuring at 5, 10, 15, 20, 25 at 330. We can calculate that based on this vector here, and we can then determine how much based on this line relative to this line, how long this line is, and then where we have to add our weights to our balancing weights to our rotor, and then test it from there. Okay, so the way that this goes is that the first thing we have to do is we have to measure the original imbalance. And so to do that, we have to create some sort of a reference on the end of the shaft. So in the shop, you'll see that on the balancing rig that we've got, there's actually an arrow that's marked on the end of the shaft. And that is just completely an arbitrary arrow. There's no, it's a reference point. It's something that we're going to base all of our measurements off of. Okay. So I've got a little balancing rig here. And that's what I've done is I've just kind of added this arrow in here. So what we have to do now is you mount the accelerometer on the bearing closest to the plane that we're reading, and then we're going to spin this thing up to speed. And what's going to happen is our accelerometer, every time this balance weight comes around to this side, our accelerometer is going to pick up that that's a peak. That's a peak amount of measurement of amplitude, and it's going to trigger our strobe light to flash. So what it will appear like, even though this thing is traveling really, really fast, going round and round and round and round, even though it's going around fast, the strobe light will make it look like it's standing still. And what it will look like is we won't be able to see visually where the imbalance is, but what will happen is the arrow that we've mounted is pointed down, and that means that this would be at a phase angle of, say, 170 degrees or something like that. So it tells us that it'll tell us how much amplitude we have, and it'll tell us that when the strobe flashes, this arrow is relatively at that position. And then we're going to go and we're going to add a trial weight. So when we add the trial weight, it's going to change this position somewhere, so that when the strobe flashes, now the arrow is looking at a different direction, and that's going to be our vector that we're going to plot the vector on now this new point, because we've mounted our trial weight and now it's looking in a different direction. So we're using this arrow just to reference where we're going to plot and how we're going to plot our vector diagram. It doesn't mean that the when I measure it that the imbalance is pointed in that direction. It means that when the imbalance hits where the accelerometer is, that's where the arrow is pointing, so we can find out that it's actually, this far off. But for the balancing part, it doesn't matter. We'll just use this number here, or this angle right here, to calculate our balancing. Okay. So that's just kind of like in a nutshell what this first picture is looking. So we're going to run this up, and it's going to tell us how much imbalance we have, and it's going to give us a phase angle. So we talked about phase. You guys know what that is now. So that's the main part. And then the next thing we're going to do is we're going to find out what that imbalance is. So they give us an example here in the book, and we'll just kind of follow along. And what it said is that we had this vector of the imbalance is 4 mils of vibration. So we see 1, 2, 3, 4. So you can see these kind of darker circles. Each one of those is representative of a mil. Okay, so 1 mil displacement, or 1/1000th of an inch shake or vibration. I'll just kind of draw, and it's kind of 1, 2, 3, 4. So that's saying 4 mils at 90 degrees. That's our first vector of our initial imbalance. Okay, so it's telling us that we have an imbalance. So then at this point, you must establish a scale that is required to identify vector t measurement for calculations later on. So what we do now is we take an actual like ruler or a scale, and on our graph paper, we'd actually measure this, and let's say that this is 2 inches long. Let's say that this is 1 inch and this is 2 inches. We actually measure it with a ruler. So what that would mean is that for every mil of displacement, one mil equals half inch, right? The reason why we do that is we're going to be doing another, and let's say that there's another, we're going to mount our trial weight and have another vector, and what we need to do is we need to measure the distance between these 2 points here. And because it's not on this nice clean line of this graph paper, we have to be able to relate this vector to this vector, proportionally calculate it out. So we'll just kind of walk through that a little bit more. So we have to establish a scale that is required to identify vector t. This can be done a few ways. In this example, measure the amplitude length of vector O in millimeters, then divide by 4 because there are 4 mils of vibration. This distinguishes how many millimeters the vector. So you guys just have to do kind of a conversion to figure this out. In the book here, they're saying that on their diagram, 1 mil of vibration on this vector chart is 7.75 millimeters. So when you determine and the more accurate you can be in measuring it, the closer you're going to get when you do your balance weight. So when you determine your scale, you can make the vectors any length if you use the same scale for every vector throughout the procedure. So as we go from now on, we can just use that same 7.75 millimeters for all of it. So the next part here, this first vector is called vector O, or vector 0. I got my eraser out. So this is vector 0, and what that stands for is O is the original. That's the original imbalance or unbalance. So now what we have to do, if we've measured that, we have to add a trial weight. So we're going to cover the calculations on deciding how much of a trial weight, but for right now, we just need to change the imbalance at least 30%. Okay. So let's say let's just follow along with their example here and weigh the weight prior to attaching it to the location of the rotor. So you guys are actually going to have to get a trial weight. We've got screws and cap screws and little brass weights that you can actually put on we have a little scale there, and you can figure out exactly how much they weigh as accurately as possible. And then you're going to add that weight at a certain location or distance from center to tell you how many ounce inches or how much actual amount of weight that we're placing. So suppose the trial weight that we added is 10 grams, and this resulted in a new amplitude of imbalance of 5 mils at 30 degrees. So the result in the original imbalance plus the trial weight is drawn in as O and T. So this O and T is, O was our original, and then the T is our trial. We added our trial weight. So O plus T equals the original plus the trial weight together, and that's what this vector is, because there's an original imbalance here. This guy here, that's our original imbalance, and then we added a trial weight, and now our new vector is in this direction here. So that's our O and our T. Okay, and that's a new vector. Now we're not going to leave the trial weight on. We're going to pull the trial weight off. The idea here is that we're trying to cancel out this original imbalance. Okay. So the next thing we're going to do is we're going to draw a vector, and this vector coming down from here to here, okay, is very specific. It has to be done in a very specific direction. It has to be from the tip of O to the tip of OT. So I actually just did that backwards. Okay, so let's clean that up. So from the tip of O, we want to draw a vector up and this way to the tip of O plus T. Okay, then the next thing we want to do is we actually want to measure this one out. So you remember in our example that we had 1 mil of change equals 7.75 millimeters. So I'm actually going to put a ruler on this, and we're going to actually physically measure that vector. And so what they came up with is that this distance here is 36. This is 36 mils. So 36 mils divided by 7.5, this vector t is equivalent to 4.46 mils of displacement. Okay, so we have to then use that vector. So that's how much, that's our actual kind of correction weight that we're going to put on there. So to calculate the correction weight, we have to use this formula on page 25. Which is the correction weight is equal to the trial weight times vector O. Okay, so the length of vector O divided by the length of vector T. So this new vector that we drew in and measured, that's vector T. So if our O was, in this case, 4, we divide it by 4.46, and then we times that by our 10 gram balance trial weight, and that's going to tell us what our correction weight, and in this example they're saying that the correction weight is going to be 8.7 grams. Okay, so the next yeah, that was vector t. I was drawing that in there. This was the math that I just did. I did it here. Sorry, I should have looked ahead and saw that. So now the last part is that we know what this vector is. So we've actually measured this vector, and we know what the length was and how much of a correction weight we need to. But what we have to do now is we have to actually measure this angle here, which in this case with the protractor is 71 degrees. So the last part is that we have to, if our original line was in this direction 90 degrees, okay, that was our original. What we have to do now is we have to find out where we put that original trial weight. And I usually, when I do this, I usually start with mounting my trial weights at 0 degrees phase. So I'd like point the arrow up to the top and then just mount the weight there. It's just easier to do the math. But we have to place the correction weight now, the one that we calculated, the 8.7 grams. We have to place that correction weight at the angle determined and at the same approximate distance from the center as the trial weight was placed. So we've kind of calculated and compared it. So if we put the trial weight at 5 inches from the center axis, we have to mount our correction weight on the same radius, or if we can't, we have to do those ounce-inch calculations that I did with you guys. I don't know if you remember when I was saying that if you have a large weight here, you can balance out that large weight with a small weight further from center. Okay, so if you can't mount the weight in the same reference point as that you did on the trial weight, so if we mounted our trial weight, out here from center, we would have to mount our correction weight somewhere on the same diameter. So always install the correction weight in the opposite direction to which the O plus T vector moved from the original imbalance vector. So if you remember, our original imbalance was in this direction, and then we put our trial weight and it moved counterclockwise that way. So when we measure this 71 degrees, we have to mount the new weight at the same diameter in the opposite direction from where our trial weight was placed. So we're not looking at original phase angles. So let's say, for example, in this case, we mounted the trial weight. I don't know. Let's say we mounted it here at 71 or at 0 degrees. So what this is saying is we have to go around this direction 71 degrees, and then we have to actually measure or mount our weight 71 degrees from where we mounted the original trial weight. Now in this example, I'm saying that this is where the weight is, and you're probably looking at this and saying, well, why, if the imbalance was that way, why would you mount the correction weight next to it? Well, maybe the trial weight was actually mounted here. Like we didn't say in here where they mounted the trial weight. So if it's here, then we would go in this direction 70. So 10, 20, 30, 40, 50, 60, 70. Okay. And at this position, that's where we would mount our trial weight, that are 8.7 grams at the same diameter that we did the original trial weight, which looks like it would probably be very close to balancing that out if the trial weight was mounted at the 0 degree. Okay, so that's all I'm gonna go through with you guys on this one. It's a very clear step-by-step kind of a procedure that you're gonna have to follow along with these steps as you go. And then you take off your trial weight, add your correction weight, spin it up, and then try it again. And then wherever you ended up with the next time around when you got to here, what you might find is that this next time that you do it, that maybe you got 2 mils. Vector O is 2 mils. Well, what you would do in that case is, instead of just making your plot smaller, what you would do is just multiply and say that instead of this being 1 mil, this 2 mils, maybe this is 1 mil and this is 2 mils, right? These vectors are just a relative length to each other. So you would expand this out a little bit. You could even go like, okay, that's 1 mil and then that's 2 mils out here. So the bigger and larger the graph that you can make on the polar graph paper, the more accurate it's going to be. Okay, so this is going to be a bit of a challenge for you guys to really wrap your heads around what's happening with this balance project, but I think you're up to it. I'm going to leave it there, and next week we're going to just look at some calculations on calculating trial weights, and then we'll get into the shop and have you guys working on this with the equipment.